All right, I'm going to walk you through what an exponential model is. And this is in the context of an upcoming homework assignment where we're going to be fitting data to a model. And actually, forget it. Hi, so we're going to be looking at today at the exponential model. It's a physical model that's used frequently for many different types of physical systems. And this is in the context of an upcoming homework assignment where we're going to be fitting data to a related model. But I want to walk through the exponential model first because it is used in so many types of physical systems that you'll encounter definitely as an engineer. All right, so this is the function that describes an exponential model. Y is essentially the variable that you're going to be wanting to understand how it's changing over time. T is the time, the elapsed time. And then y, we call that y naught. Y sub 0 is essentially the initial value. And k is a rate constant. It has dimensions of 1 over time. And for those of you that are not so familiar with exponents, E is essentially a constant, 2.71828. It has an infinite number of digits to describe it. And it has some very interesting properties that are used, and that's why it's used in this case. If you've taken a class in calculus, hopefully you understand, or pre-calculus, hopefully you already have some concept of what it is. All right, so I'm going to go through a couple of the interesting properties of exponential models. The first of which is that the rate of change of y is proportional to the value of y. So what do you mean exactly by that? If you look at the rate of change of y, delta y over delta t, in other words, how fast is y changing with respect to time? That's going to be proportional to the value of y times our rate constant. So you can see where t in this case equals, well, you may not realize it, but this is delta y over delta t is the slope of a line that would be tangent to our exponential model curve. And as you get, the time goes up higher, in other words, actually in this case, as y value gets higher, the slope is going to be steeper. So delta y in this case is the slope of this line. That would be essentially at a value of around 250. But then when you get up to delta y, a y value of about 500, that slope is going to be twice as high because it's proportional to the y value. All right, so we're also going to look at the time to double for the exponential model. In other words, what is the elapsed time that it takes for a parameter y, in this case, to go to double? And that is a direct relation to this value of k. So if we start at time 0, we have a y of 100. We go out here to time of about 3.5. You see that the y value is doubled. Now if we go to 400, you can see that the time is now about around 7. So it was that 3.5 times 2. So the time for the value to double goes up at a constant, over a constant period. And it tells here that the doubling rate is essentially 0.69 divided by our value k. Now for values of k less than 0, it's not doubling, it's actually declining, and we call that the half-life. It's the time to reach half the value. It's also equal to that same 0.69 over k value. So again, as I was just mentioning, this exponential model can be used to represent growth. In other words, increases in y, and also decay, decreases in y. So what types of models are describable? This is kind of a parable about the exponential model. Imagine you have a grain of rice on the first square of your chessboard, and then you put 2 on this square, and then you put 4 on the third square, and then you get out to 64 squares. In other words, you do that on and on through all of the squares. There's 64 in a chessboard. How many grains of rice do you think you'd end up with? Well, in fact, you'd end up with a lot more than you probably thought of. You end up with 9 million trillion rice grains on the last square. You see here, 9 million. So you see one from 1, 2 to 4 to 8, 9 million trillion. So the exponential model can cause growth at a very rapid rate. And you can see how it's growing more and more rapidly as the value itself is getting higher. All right. So what other physical systems grow an exponential model? Population dynamics. So if you put a bunch of rabbits in, they're going to, if you have 2 of them, they grow initially very slowly, but you get up to 10, 20, 40 rabbits, and they're going to start, the population will grow much more rapidly. This is essentially the same thing with humans. And you can see that essentially here's a population increase over time. We get into the 20th century and things are kind of blown out of control. Actually, money can work the same way. Unfortunately, our interest rates are so low at the current time, it's hard to see much growth at all. But if you have an interest-bearing account, that is essentially an exponential model as well. Here's a case of bacteria growing, and you can see the time. So you start out with 1, splits, 2, splits again. After a while, the rate of growth grows much faster. Okay, that's exponential growth. That's a great example. Water quality in a stirred tank. If you put in essentially an initial amount and then stir it up and let it out over time, so you have your mixed product coming out of this stirred tank. As the more and more you let out of this thing, the concentration is going to decline over time. So that would also be a case. Water quality in a relatively well-mixed water body after a spill, same thing. As long as you have an outlet from that water body, it's going to decline over time. That doesn't even mean that the chemicals is essentially organically being decayed. It means just that that's just a factor of what happens when you let water out of the system and dilute it with incoming water. Other systems, acoustic absorption, charge on discharging capacitor, damping of vibrations, oil well production, all modeled with exponential models. So it's great, terrific model used frequently in many different types of physical systems.